So a hydraulic jack, like one pictured here in the image, allows a person to very easily lift up a car. So how does a hydraulic jack like this work? That's what we're going to look at today. And what does the word hydraulic mean? Well, hydraulic means water. Okay. Meaning that there's some fluid in this thing. Now, normally water isn't used; they use an oil because it doesn't rust the parts, and it's just lubricates the flowing parts. But the same principle can be illustrated with water. Okay. So if I had a sealed syringe, okay, so meaning the tip of syringe, this is my syringe, it's got water, and the water's got a couple air bubbles in it. And I were to squeeze on it, okay, maybe drive this syringe in a little bit, would the air bubbles see any change? Or would they change? Would they get bigger, stay the same, get smaller? Okay. Well, when you squeeze on it, they actually would get smaller and probably detach from the sides and float up. Okay. Why does that happen? Okay. Well, it's because when we squeezed on that piston, we created pressure, and that pressure squeezed on the air bubbles in turn and caused them to decrease. Okay, so when we push on when we apply a force to an area, and this is like on a piston. So this when we think of a piston, we're going to be thinking of a syringe where we've got a tightly fitting kind of circular plate that seals when we push in on this. So this is my piston here, and the area that we're going to be looking at is the area of the piston itself, so the circular area, so when we squeeze on that, we're going to generate pressure. Okay, and when we squeeze on that and generate pressure, that pressure increases everywhere in contact with the fluid. Okay, or even if the air bubble was preventing contact with the wall, the pressure on the air would go up, and then the pressure on the wall would go up. So the pressure everywhere inside that confined space goes up. This is Pascal's principle. Basically what it says is changes in the fluid pressure are transferred to every point in the fluid undiminished. Okay, and we're going to go through what undiminished means in a little bit. So basically when I apply a pressure, okay, so right now there's pressure and it increases as I go down the tube because of the depth, right? As you go down in a fluid, the depth causes the pressure to increase. Okay, if I apply 2 pascals of pressure to the piston, that 2 pascals everywhere is going to increase by 2 pascals. So that's where that red line is showing that everywhere is increasing by the same amount. Okay. So undiminished, that little bit right there. So what this means is the pressure everywhere goes up by exactly the amount added to the pressure at by the piston. It's not diluted by more area. And what I mean is, okay, so this piston, I really should have a better image for this, but if I apply 10 newtons per meter, 10 newtons over a 2 meter Pascal piston, okay, then the pressure everywhere goes up by how much? Okay, 10 newtons over 2 meters squared, that's the area of my piston. So force divided by area gives me 5, so the pressure everywhere goes up by 5 pascals. Okay? Now, if I apply that same force to the same size diameter piston, well, sort of the same size piston, cover or whatever, they're both 2 meters. Okay, the pressure in both of these is going to go up everywhere by that same 5 pascals. The fact that this has more area in it because it's longer isn't going to dilute that pressure anymore. That's really what I'm trying to get to, the nitty-gritty of this. It's not diluted by more area. So the pressure in both of these would go up by 5 pascals. Okay. Now what about this piston here? This is going to create a pressure of 5 pascals. What pressure is this going to create? 10 newtons divided by 1 meter squared gives me 10 pascals. Okay, and Is that 10 pascals because there's less area on the walls here, okay, or because there's less cross-sectional area on the piston here, okay, less cross-sectional? It's because of the area here. It's not because there's less area on the walls here, okay. All right. So now if I connect two piston plugs in a pipe, if I push on this piston here, that's going to raise the pressure everywhere in here, including the pressure on the piston plug here, okay, which is going to cause that piston plug to move to the right with everything else, okay, trying to balance out the pressures, okay. So I can use one piston plug to move another piston plug. What if I push down like this? Will this piston still move up? Okay, it will, okay. If I push down on here, the pressure everywhere on the walls is going to increase, okay, including the upward pressure here. So when I push down here, I'm creating upward pressure here, and that's going to cause that piston to go up, okay? Or in other words, the water's got to go somewhere when you push down, okay? So let's say I push with 20 newtons of force on a piston plug that's 1/4 of a meter squared. What is the applied pressure? 20 newtons divided by 1/4 of a meter squared gives me 80 newtons per meter squared, 80 pascals. Okay, how much pressure is going to be applied to the other piston here? Okay, if we're creating 80 pascals of pressure here, and that's going all over the walls here, okay, is the pressure here going to increase by more or less or the same as 80? Okay, well, I tried to trip you up by saying all over the walls here. The pressure is going to go up by 80 pascals as well. Okay, now how much force does this exert if this piston plug is the same size as this piston plug? Okay, well, it's going to be 20 newtons. Okay, 80 pascals times 0.25 meters squared gives me 20 newtons. Okay, so I could set this on here if these were equal sized plugs, okay, and this would balance. Okay, now would this balance? Okay, the answer is no. The question is, which way would this piston go? Would this piston fall, or stay the same, or rise? Or I told you it wouldn't stay the same. Would this piston fall or rise? Okay, well, it actually would rise, and we're going to explain why. Okay, which side would you want to push on it with 20 newtons of force to create the most pressure? Okay, do you want it over the large area, or do you want it over the small area to create the most pressure? Okay, you want to push on the small area to create the most pressure. Concentrate that force. Okay, so let's break it down physics style. How much pressure am I generating when I push down with this? Well, 80 pascals again. Okay, so 80 pascals of pressure here. So this is 80 newtons per meter squared. 80 newtons per meter squared. So on this piston here, I've got half a meter squared. At 80 newtons per meter squared, how many newtons of force do I get when I it would be 40 newtons. Okay, both of these give me a pressure of 80 newtons. 20 divided by 0.25 gives me 80 pascals. Okay, 40 divided by 0.5 gives me 80 pascals. The pressure is the same at both locations, but I get a greater force. Okay, so force over area equals pressure equals force over area. All right, looking at the numbers, 20 over 0.25, F1 over A1 equals F2 over A2. Okay, 20 divided by 0.25 gives me 80, and 0.4 divided by 0.5 gives me 80 as well. Okay, so what happens? The piston moves if I've got only 20 newtons of force here. And so when I do that, I get work done, okay? And so when I do that, I get work done. This is like the hydraulic, how the hydraulic jack works, by the way. This is my input force, which is much less than my output force, and in a car jack it's multiplied by even more. So when I do this, I do work, and I can't get more work out than I put in. So the trade-off is, even though I get more force out, just like in simple machines, I get less distance. Okay, I get more output force, but I lose distance. There's always a trade-off. So 20 times 2 gives me 40 Newton meters, 40 joules of work in. Okay, 40 newtons times 1 meter gives me 40 Newton meters, or 40 joules out. Okay, remember, force times distance equals force times distance. Work in equals work out. Okay, we can't break conservation of energy. That's a big no-no. Okay, so these hydraulic pistons are used in all kinds of machinery, heavy construction machinery. I just used a device the other day to dig some post holes to put a fence in, and it used these hydraulic pistons to raise and lower an arm and to spin an auger to dig holes. And these are those pistons, and as you push, as hydraulic fluid is pumped in, it pushes that piston out and causes this arm to move. Okay, so in this case, the hydraulic fluid is pumped in, and it pushes these pistons out, and it causes the back of the truck to dump. Okay, so and they're connected by these flexible hoses, which is really cool that you can do that because the arms need to move and flex and things like that. Okay, so this is how a hydraulic jack works. You've got a small piston and that you pump on. So this is the lever that you pump. So when you pump down, you squeeze fluid, and it goes towards this larger diameter piston that pushes the car up. And so it's the fact that this piston's larger that gives you a greater output force than you put in. Okay. So your car brakes use hydraulic fluid and pistons to stop your car. This is everyday cars, and there's all kinds of things to learn about that. So if you want to make it so that a greater force is put on the car brake than what you apply to the foot pedal, okay, do you want should the larger piston be at the pedal or the brake? Okay, if you want the larger pressure to be at the brake, okay, should be at the brake itself, and those are larger pistons than the one that you push on. Although there's some more things going into that. Okay, so let's work a math problem with this. This is a little bit more mathy than the ones we've been doing. So we've got piston A, it's got a radius. Now here it's a radius. Okay, and when we deal with pressure, we got to deal with areas, not radius. What's the area of a circle? Pi r squared. Okay, so this piston's got a radius of 0.7. This piston has a radius of 2.5 meters. So we're going to exert a force of 10 newtons at this piston. Okay, what's the applied pressure? Okay, and what's the force applied to piston 2? Okay, so this is how we work that. So first off, we find the area of piston 1, so pi r squared. So the radius of piston 1 was 0.7, so the pi r squared gives us 1.54. Okay, the pressure that we're generating is equal to force over area. Okay, so that's 10 newtons of force. Okay, divided by 1.54 meters squared gives us a pressure of 6.5 pascals. So now we've done the left piston. So now we know how to do the right piston. Okay, so force 2 is what we're trying to find. Okay, we know that the area 2 is equal to pi r squared again. Now this piston had an area of 2.5 square meters, so it has a much larger area of 19.6 meters squared. Okay, then we're going to use the pressure equation to figure out the force at piston 2. Okay, so the pressure at piston 2 is the same as generated at piston 1. The pressures are the same. The force and areas are different. Okay, that's what you got to keep in mind. The pressures are the same. the force in area is different. So the pressure is 6.5. Okay, that's how much pressure is being exerted on piston 2. We're looking for the force, and the area we just calculated was 19.6. Okay, multiplying through, we get that the force on piston 2 was 128 newtons. Now let's sanity check this. So at piston 2, we had a much larger area, okay, which means we have a much larger force. So that's good. The other way you could have set this up to find the force at 2 is you could have said F1 over A1 equals F2 over A2. Okay, and you could have set it up this way and gotten the exact same answer. Okay, so here's another example of hydraulics. So here we've got the car. See, this guy is pretty cool. He's got his head leaning hard left. And he's got a remote control for his car. So bouncing it up. And people spend thousands of dollars to put hydraulics in their car and all that malarkey, but whatever. So that is it for today. Do worksheet 9-5, and we will see you soon, if you're in person anyway.